Today's objectives determine the mass moment of inertia of a rigid body or a system of rigid bodies. In statics, chapter 9 and chapter 10, we have studied about area moment of inertia. And the area moment of inertia is because of the geometric shape of the object, and it is the resistance to bending. So the shape which has the area which is farther away distributed from the axis of bending has higher resistance to bending. So if you look at all these different examples, then the I section they all have the same area, by the way, but the I section in the first example has the area which is distributed away from the axis of bending, away from the center of mass, and thereby it offers the highest resistance to bending. And this is what we have studied in statics. I strongly advise that you go through the concept of center of gravity and area moment of inertia before we continue learning chapter 17, that is mass moment of inertia, because the topics are related. Now, what is inertia in general? So consider this example where there is a mass of the block of mass m which is subjected to force F. Now, when the force is applied to block, the force will have the tendency for the block to have some acceleration as per Newton's second law of motion, F is equal to ma. Now, there is a property of the body which resists this acceleration, and this property is called inertia. So inertia is resistance to acceleration for this linear system. If you extend this concept of inertia to rotational motion, such as this circular disc in this example is connected to the shaft, is mounted on the shaft, and when the external torque T is applied to the circular disc, this torque will try to have some angular velocity or rate of change of angular velocity for the circular disc. So this torque tries to give some angular acceleration to the circular disc, but there is a property of the body that resists angular acceleration, and this property is called mass moment of inertia, or MMI. So mass moment of inertia is applicable to rotational objects, and it is resistance to angular acceleration. So let's look at the reading quiz. So mass moment of inertia is a measure of the resistance of a body to blank. Options are translation motion, deformation, angular acceleration, or impulsive motion. And the correct answer is C, angular acceleration. Second question, mass moment of inertia is always negative, positive, has an integer value, or zero about an axis perpendicular to the plane of motion. You should be able to answer this question later once we see this equation in the chapter, but right now I give you the answer, and the answer is it's always a positive quantity. So what are the applications of moment of inertia? So look at this large flywheel in the picture, which is connected to a large metal cutter. So this big wheel is a flywheel, and this is the metal cutter. Now the flywheel mass is used to help provide a uniform motion to the cutting blade. The function of the flywheel in this machine is to maintain the constant motion for the cutting blade. What property of the flywheel is most important for this application? How can we determine a value for this property? So the property of the flywheel that is most important for this application is its moment of inertia. And how do we calculate this value? That we'll see shortly in the lecture. And why is the most mass of the flywheel located near the flywheel circumference? So if you look at the weight mass distribution in flywheel, you will see these pockets, they are empty, so there is no mass in that portion, but majority of the mass of the flywheel is farther away from the axis of rotation. Why is it done that way? So if the mass is distributed away from the center, will it result in higher moment of inertia or less moment of inertia? Just think about it. You'll get the answer soon. So I have this video from YouTube which explains what is flywheel and its application.
what is a flywheel? Consider a foot-operated sewing machine. It consists of two wheels, one big and the other small. The wheels are connected by a rope. When motion is imparted to the bigger wheel, the rope transfers this motion to the smaller wheel. This smaller wheel acts as a pulley and runs the sewing machine. We see that even when we stop supplying driving force to the bigger wheels, it still continues to run for a short time because of the inertia it possesses. Thus, flywheel is a device that acts as an energy reservoir by storing and supplying mechanical energy when required. Flywheel is used in reciprocating engines to store some amount of energy during the power stroke and deliver it back during the intake stroke of the next cycle. Similarly, it's used in toy cars, gyroscopes, etc. The related term is
And then there is, I'll just show you this video, not the entire video, but short portion of the video which shows the real flywheel mounted on a tractor. Okay, so in this case, the flywheel is used to start the engine. Okay, and that big rotating disc is a flywheel. Now, this is one more application of oil pump rig. So, crank in the oil pump rig undergoes rotation. So, this is the crank, by the way. It undergoes rotation about a fixed axis that is not at its mass center. The crank develops kinetic energy directly related to its mass moment of inertia. As the crank rotates, its kinetic energy is converted to potential energy and vice versa. You can watch this video which explains this operation of the oil pump rig. And yeah, this is the oil pump rig in operation. This rotating part is crank, and you can see that it's not rotated from its center of mass, but it's rotated from an axis which is away from its center of mass. Is the mass moment of inertia of the crank about its axis of rotation smaller or larger than its moment of inertia about its center of mass? What do you think about it? So let me reframe the question. So this is another figure where the center of mass of the crank, that means this portion only, is somewhere here, and but it's being rotated from the point which is away from the center of mass. So the axis of rotation does not pass to the center of mass. So when it is done in this way, will it have high moment of inertia or less moment of inertia? And the correct answer is it will have high moment of inertia. For any object, if you rotate that object about an axis that passes through its center of mass, then it will have the minimum moment of inertia from that point, from that axis. But if the axis of rotation does not pass through mass, center of mass, then the moment of inertia is always more than minimum moment of inertia. So consider a rigid body with center of mass at G. So this is the center of mass. It is free to rotate about Z axis, which passes through mass center of mass. Now if we apply a torque T about the Z axis, as you can see in the figure, the body begins to rotate with an angular acceleration alpha. So in that case, the torque and angular acceleration alpha are related by this equation T is equal to I alpha. In this equation, I is the mass moment of inertia about Z axis. In fact, you can actually compare this equation to the F equal to ma equation for linear motion. There is a direct similarity between these two equations, where A is linear acceleration, alpha is angular acceleration, F is force, then its equivalent for rotational motion is torque, m is mass for linear motion, while I is moment of inertia or resistance to angular acceleration. So the moment of inertia is a property that measures the resistance of the body to angular acceleration. The MMI is often used when analyzing rotational motions. Now in this slide we will see how to calculate it. So consider a rigid body and the arbitrary axis P shown in the figure. The moment of inertia about the P axis can be defined using integral of r squared dm, where dm is small elemental mass. We consider the small portion of mass in the entire body located at distance r from the axis of rotation. Then moment of inertia of this small mass only is r square dm. So the moment of inertia is the product of the square of the distance of the mass from the axis of rotation with its mass. So it's r square dm, but it's only for small mass. Then to calculate the moment of inertia of the entire object, we need to integrate over the mass. So it's integral of mass r square dm. Now the mass moment of inertia is always a positive quantity and has a unit of kilogram meter square or slug feet square. You know, its unit has two terms into it. One is r square, where r is distance, so it is either meter square or feet square, and the second term is dm, which is for mass, so mass is either in kilogram or slugs. So the unit of moment of inertia is kilogram meter square for SI system and slug feet square for FPS system. And it's always a positive quantity because it is the product of distance square with mass. Now neither the mass nor the distance is zero, like can be negative, by the way. So it's always positive quantity. So look at this option, in which case on left or right it is easy to rotate this rod with the weights attached to it. So in this example, on the left hand side, the distance between the rod, the weights are mounted close to the center of mass, and a person tries to hold the rod and rotate in this direction. And in the second case, the weights are farther away from the center of mass and person tries to rotate, which case it is easy to rotate. And the correct answer is it's easy to rotate in the left case and it's difficult to rotate in right case, because in right case the moment of inertia is high, because just in the previous slide we have seen equation for moment of inertia is r square dm. So farther the distance away from the center of mass, higher will be the moment of inertia. Same but different way of rotation, same example. In this case, if you hold the weight like this and try to rotate it, then it has low moment of inertia, so it's relatively easy to rotate compared to when weights are farther away and you try to rotate, it has high moment of inertia. The figures in this example show the mass moment of inertia formulations for two shapes commonly used when working with three-dimensional bodies. These shapes are often used as differential element being integrated over an entire body. So in this example, we have a thin circular disc, and this is the x-axis and y, so the plane of the disc is parallel to xy plane, and z-axis is perpendicular to the plane of the disc, and g is the mass center of the disc. Disc has radius r. So if what is the moment of inertia of the circular disc? Its value about x-axis. So if you try to rotate this disc with respect to x, that is in this direction, or with respect to y, that is in this direction, circular direction, then it offers the moment of inertia 1/4 times mr square. And its moment of inertia about z-axis is 1/2 mr square. Don't think about this for now, we will come back to this discussion later, but only remember that its moment of inertia about x and y is same, which is 1/4 mr square, and about z-axis is 1/2 mr square, while that of a rectangular plate or thin plate with dimensions a, b for xy dimension, so a is the length along x and b is the length along y, and the thickness can be neglected. That's why we call it thin plate. So we don't worry about the thickness of the plate. And G is the center of mass for the for the rectangular plate, and axis Z is perpendicular to the xy plane. So its moment of inertia about x is 1 by 12 mb square. Its about y is 1 by 12 ma square, and about z is 1 by 12 m a square plus b square. If you look at both this example, you will notice that moment of inertia about z-axis in both the cases is highest. That means if you try to rotate both these objects about z-axis, you need to provide the maximum or larger torque compared to you try to rotate them about x or y axis. So let's look at one example with some values for the application. So the application in this case is we have a thin circular disk of radius r, and the angular velocity of the disk should increase to 100 radians per second in 10 seconds starting from rest. So this is omega. So omega should change from 0 to 100 in 10 seconds. Mass of the disk is 20 kilogram. Radius of the disk is 0.3 meters. What should be the torque required from the motor? So let's say we need to rotate this disk using an electric motor, and our job is to select the right size of electric motor so that when we attach the disk to the electric motor and when we give the electrical energy to the motor, this disk will have angular velocity of 100 radians per second in 10 seconds. How do we make this calculation? This is very practical application, and let's see how do we do it. So we apply this equation, torque T is equal to I alpha, where I is the moment of inertia, alpha is the angular acceleration. This is circular disk, and we try to rotate this with respect to z-axis. So its moment of inertia can be calculated using this formula, which is 1/2 mr square. So you substitute these numbers. So 1/2 is 0.5, mass of the disk is 20, r is 0.3 square. So this is moment of inertia of the disk. Second term in this equation is alpha, angular acceleration, which is rate of change of angular velocity divided by time. So it's 100 minus 0 because it's starting from rest divided by time, which is 10 seconds. So when you substitute I and alpha into the equation of torque and calculate it, its value is 9 Newton meter. That means we need an electric motor with at least 9 Newton meter torque. If the motor has torque less than 9 Newton meter, we will not have this 100 radians per second in 10 seconds. Now, once we calculate the torque, the next practical thing to do is go to the manufacturer's website and look at the data sheet for different electric motors. Now, this data sheet includes information about speed, torque, and power for in the form of a chart and as well as in the form of this table. Now, the torque values are given in inch pound or foot pound in Newton meter. We have the answer in Newton meter, which is 9 Newton meter. And we need to select the motor with the least horsepower, and the horsepower is listed here. So if you look at the table, you will notice that this particular motor, like this specification, has torque which is 10.7, which is slightly more than our requirement, so it works, and it has the least horsepower of 1.5 HP from the available selection. So we can select this particular model of the motor with the horsepower 1.5, torque 10.9, and RPM is 1000. And that's what most engineers do when they do the motor selection. Now, in the previous example, like in this example, we have just considered the motor to rotate a simple circular disc. But on a broader scale, the same concept can be applied for any motor selection. Now, be that motor for robots, or that motor for any circular saw or any circular machine, or that motor is for Tesla car, because Tesla is electric car and it does not have any internal combustion engine, but all the wheels are driven by electric motors. So if you look at the specification sheet for Tesla, then these cars accelerate from 0 to 60 miles in 3.2 seconds. So this is speed. So 0 to 60 in 3.2 seconds. So you can actually calculate the acceleration for Tesla, which is 60 minus 0 divided by 3.2. Okay. So that is the linear acceleration. And if you know the diameter of the wheel, you can convert the linear acceleration into angular acceleration. We have studied this in previous chapter, that A is equal to r alpha, where r is the radius of the disk or radius of the tire, and alpha is the angular acceleration. So once you have the angular acceleration and you know the moment of inertia of the tire, you can actually calculate the required torque for the motor, and that same motor can be given to all four wheels, and that will result in the required speed from 0 to 60 in 3.2 seconds. So this is the broader application of moment of inertia. So it's a very useful topic for designing machines involving rotating parts or selection of motors. Now, for standard shapes, moment of inertia is equations are already given to you in the form of this equation chart here. You don't have to memorize it. This is the exact sheet that you will get for your final exam along with other equations. However, I suggest that you familiarize yourself with the equations on this page, and also you know different variables. For example, if you need to calculate the moment of inertia of cylinder where G is the center of mass about, let's say, x-axis or y-axis, then it's 1 by 12 m 3r square plus h square, where h is the height of the cylinder. Similarly, moment of inertia for a slender rod about x or y axis passing through its center of mass G can be given by 1 by 12 ml square. And the same moment of inertia for axis x dash and y dash, which are parallel to x and y, but they do not pass through the center of mass, it can be calculated using this equation 1 by 3 ml square. So yeah, just go spend some time to look at this equation sheet, and yeah, we'll make use of it when we solve problems. So let's look into the slender rod in more detail. In fact, this is what we will use in one of the in-class exercise problems. So in this example, G is the center of mass, x-axis is here, y is here, and z is perpendicular to xy plane. We neglect the thickness of the rod, that's why we call it slender rod. So if you need to rotate this rod in this direction as shown in the arrow about x-axis, then the moment of inertia is 1 by 12 ml square. Okay. And then if you need to rotate this about x dash axis, which is parallel to x axis, then its moment of inertia is 1 by 3 ml square. So what does it mean? That the rod will have, now 1 by 3 is bigger number than 1 by 12. So 1 by 3 is greater than 1 by 12. That means the moment of inertia about x dash is more than moment of inertia about x. But what does it mean practically? You can actually do this little experiment at your home. So if you have a slender rod, try to hold the rod roughly from the center and rotate as shown in the figure. So try to rotate it in this direction, like perpendicular to the PowerPoint slide in this example. So if you try to rotate this rod in about that axis by holding it from the center of mass, then its moment of inertia is 1 by 12 ml square. But then try to rotate this from either end, left or right, and you will feel that it's more heavy and you need to apply more energy or torque to have the same rotation, because it has high resistance to rotation, a rotational acceleration, because its moment of inertia is now 1 by 3 ml square. So for what option it is easy to rotate the disk? On the left side, we try to rotate the disk about z-axis, passing through center of mass. In right case, we try to rotate the disk about x-axis, again passing through center of mass. And think about it before I give you the answer. And the correct answer is it's easy to rotate about z-axis because its moment of inertia is only half mr square. It's easy to rotate about x-axis because its moment of inertia is a quarter mr square, while the moment of inertia about z-axis is half mr square. So yes, on right side it's easy to rotate compared to left side. Now if you come across a shape which is not a standard shape, that means it's not a circular disc or rod or a thin rectangular plate or sphere at some type of like irregular shape, then you can still calculate the moment of inertia by applying the known shape and integrating it over the length. You can either use cell element or disk element and calculate the moment of inertia. Parallel axis theorem. So if the mass moment of inertia of the body about an axis passing through the body's mass center is known, then the moment of inertia about any other parallel axis may be determined using the parallel axis theorem. And as per this theorem, moment of inertia about any axis is moment of inertia about the axis passing through center of mass plus md square, where m is the mass of the body and d is the distance between two axes. So ig is the moment of inertia about the body's mass center, m is mass of the body, and d is the perpendicular distance between two parallel axes. Let's apply this equation to one problem. So in this case, again, we know the moment of inertia of the circular disk passing through g about z axis is 1/2 mr square. Now, instead of rotating this disk about the z-axis, let's say we would like to rotate this disk about z dash axis, which is parallel to z, but it does not pass through the center of mass. So what is the moment of inertia about z dash? So in that case, we can apply the parallel axis theorem. So the first step is calculate the moment of inertia about axis, which is parallel to z dash and passes through the center of mass, and that is 1/2 mr square. So that is Ig plus m, which is mass of this, multiplied by d square, which is the distance between these two axes, z and z dash, and that distance is r. So it's 1/2 mr square plus mr square, and if you do that math, you will get moment of inertia about z dash axis or z dash axis is 3/2 mr square, which is 1/2 plus 1, that is 3/2. Okay, so that's the equation for, so that's the concept of parallel axis theorem. There is one more thing that you should remember, that when we have a composite body, that means the rigid body is not made up of single shape, but it's made up of multiple standard shapes. In this example, the rigid body this is the single body, but which is made up of cube and cylinder. How do we calculate the moment of inertia of the combined, like a single rigid body here, which is combination of two different shapes? So in that case, we need to we can determine the moment of inertia of the rigid body by algebraically adding together all the mass moment of inertia found about the same axis of the different shapes. That means in this case, you need to find out the moment of inertia of the entire rigid body. Then its moment of inertia of, let's say, about the axis which is perpendicular to the cross section of the objects, and it's in this way. So it's z-axis. Then the moment of inertia of the rigid body is moment of inertia of the cube plus cylinder, which is simple. So it's algebraic addition. Now consider this example on right, where we have a cube, but now we have the hole through the cube. So its moment of inertia is the moment of inertia of the cube minus the moment of inertia of the cylinder, because this cylinder actually is considered as a hole. Okay, or in other words, hole is considered as a cylinder. So see the algebraic addition. So if the parts are joined together, their volumes are added, then you use plus sign. When the volume is removed, then you use minus sign. And this is one the concept of radius of gyration. So the mass moment of inertia of a rigid body about a specific axis can be defined using the radius of gyration k. The radius of gyration has the unit of length, and its measure of the distribution of the body's mass about the axis at which the moment of inertia is defined. Anyways, just go through this paragraph. I'll give you a simple explanation in the next slide. So the equation for radius of gyration is mk square, where k is the radius of gyration and I is moment of inertia, m is the mass. So for any object, if you know its moment of inertia and mass, you can calculate radius of gyration by taking the square root of the uh, division of moment of inertia with mass. Now, I'll try to explain that concept with an example. So consider the circular disk with mass 10 kilogram and radius 0.1 meters, and we try to rotate this disk with respect to this red line, which is an axis perpendicular to the plane and passes through the center of mass. So it's z-axis, and moment of inertia about z-axis is 1/2 mr square. Now we know the mass of the disk, which is 10 kilogram. We know radius, so substitute these numbers and we'll get the moment of inertia of 0.05 kilogram meter square. Now instead of circular disk, we replace this disk by a point mass which has the same value of 10 kilogram, but it does not have any shape or size. So it's 10 kilogram mass which is located at some distance k away from the axis of rotation, and we would like to know what should be the value of k so that point mass will have the same moment of inertia as that of circular disk. So in other words, if you replace the circular disk by a point mass and still would like to maintain the moment of inertia of 0.05 kg per kg meter square, at what distance this mass should be located away from the axis of rotation? Now, what is the moment of inertia of this point mass? It's mk square. So in this equation, you substitute I is equal to 0.05, m is equal to 10 kilogram, and calculate the value of k, and that number is 0.07 meters, and that is the radius of gyration. It's very useful because for any, let's say, dynamics problem, if you know the mass of the body and its radius of gyration, it's very easy to calculate moment of inertia. Because if you do not know the radius of gyration, then you have to calculate moment of inertia using this equation if it is standard shape, or you need to do some integration over the mass if it is non-standard shape. But if you know its radius of gyration, then it's very easy to calculate moment of inertia. So I is equal to mk square. We will make use of this in some in-class exercise problems. And one last thing before we talk about in-class exercise is how to calculate mass if you know the size of a rigid body, x, y, and z dimensions, and you know the density. So in this example, this is the aluminum cube whose size is 0.5 by 0.5 by 0.5 meter. That means this length is 0.5, this height is 0.5, and this width is also 0.5. And this is aluminum cube, so its density is 2700 kilogram per meter cube. What is the mass of this cube? How will you calculate the mass of this cube? So mass of the cube can be calculated by multiplying volume with density. So volume of the cube is length, width, height, multiplied by density is 2700, and the mass of the cube is 339 kilogram. Okay, so yeah, that's it. And now for the next part of the video, we will do some in-class exercise.